Hello, young chemists. So I'm a little bit concerned that some of you might not be that comfortable with some of the math that you saw in the last lesson. And so I really want to focus on that a little bit with you. The thing is that this math, this ability to solve the problems, it's really the heart of what we're doing. We're focusing on skills that you can carry with you into the physics class next year, that you can carry with you to the university level, to pre-med, to engineering. So the gas laws are great and everything, and it explains how the air in the tire has a certain pressure and why the tires get flat sometimes, but the math skills that you gain here is the key thing that's going to carry you to something else. So it is important, even if it might not be our favorite thing to do. So we've already been talking about the pressure, volume, temperature, the things that we measure. The pressure of the air around us is called the atmospheric pressure. And there is something called standard temperature and pressure, STP. If you see a problem that references this STP conditions, it means that the pressure is at 1 atmosphere and the temperature is at 0 degrees, which is also 273 Kelvin. Atmospheric pressure is different in different areas. At high elevations, there's lower pressure, and if you're down in a valley at low elevations, you'll experience a higher atmospheric pressure. And we talked earlier in a different lesson about how a barometer is the piece of equipment that helps us measure the pressure of the air around us. So we can measure the pressure of the air around us, and we can also measure the pressure of a contained gas. And then we talked about Boyle's law, and you worked some problems with this formula. You did a couple of graphs and saw that Boyle's law is an indirect proportion. Charles' law is a direct proportion. And so today we're going to look at really comparing the mathematical relationships between a direct proportion and an indirect proportion. And this is a skill that's pretty key. So I gave you this formula for Boyle's law, and you did a good job solving problems with it, but we never looked at it too closely, and so I want to kind of back up and look at some of the mathy math, the math that a math teacher would think about when they look at inverse relationships and direct proportions. So with an inverse proportion, this is the formula here that they would give you and say this is the formula for an inverse proportion. As one value goes up, the other one goes down. And the formula is y is equal to k, and k is a constant over x. And that k is something that they call a constant of proportionality. So no matter what y is, in order to get x, you'd take k, this constant, and you'd divide by x to get y. And so this is the formula for something that is an inverse proportion, and that's what we were dealing with when we had Boyle's law. And one of the things is that hard for some students because they just aren't that comfortable with the math is they look at this and they think, well, I don't see how that's anything to do with an inverse or what we call an indirect proportion. And I understand that. One of the things that you can do if you struggle with the math is to play around with the math a little bit. So if you take this formula and you say, well, how is that a formula for an indirect or an inverse proportion? Let's give k, the constant, some kind of a random number. So I'm going to give the constant a number of 20, and it's just a number I picked. Okay, I didn't want anything too small and I don't want anything too big. And so if I look at that and I see that k is 20, then I can pick a number for y. And so I'm going to say, okay, y, I'm just going to give it a number. It's going to be 5. So I've got this formula, y is equal to k over x, and I'm substituting in 20 for my k. So 20 divided by x being y, if my y is 5, then 20 divided by something is 5, then that means that x is 4. So there I have some numbers that actually work in the formula. Now if I take my 5, my y, and I want to make it go up, I'm going to want to increase my y. So I'm going to just randomly say, let's say y is equal to 10. Now I've got my formula. I'm going to put 10 in. 10 is equal to 20 over x, and this time x is going to be equal to 2. 20 divided by 2 is 10. Well, look what happened. I increased y, and what happened to the x? It decreased. Oh, look, it's an indirect relationship. Let's try it again. Let's see if I can see another example. Instead of bringing my y higher, I'm going to make my y go down. So I'm going to say y is equal to 2. I'm just going to pick a lower number. So 2 is equal to 20 over x. I'm solving for x. 20 divided by something has to be 2, and that something's going to be a 10. Oh, look. I lowered my y, and what happened to the x? It did go up. So I can just play with that a little bit, put a few numbers in, and see that, yeah, that is a relationship that's an indirect proportion. So that's what math gives us when they say, here's a formula for an inverse proportion. And in chemistry, we don't really care what the constant is. What we want to be able to do is we want to be able to make predictions. So if I have two values, a y and an x, I want to solve and get the constant on one side of that equation. So in order to do that, I'm going to multiply both sides of this by x. So the x's cancel here, and I'm going to get xy is equal to k, which is the constant. And what that means is that if I change any of the values for either x or y, so I could have an initial x and initial y, and I change one of them, the other's going to change in such a way that after the change, I can multiply x and y together, and I'm still going to get that same constant. And the truth is, in chemistry, we don't really want to know the constant. What we did with Boyle's law is we used this formula. We said we're going to take the pressure and the volume and multiply it together, and then we would get a constant that we're not interested in, so we pulled that right out of the equation, and we set that equal to the pressure and the volume after our change. And so from this, we really end up with then our Boyle's law formula, which you've used. So you have this automatic, here's what a formula looks for an indirect proportion, and out of that we have Boyle's law, and you solve some problems with that. Now we know Charles' law is a direct portion, and so when we just look at the math, we're going to be in a math class for a minute. They say, okay, direct proportion, when one changes the other, like a young tree, the older it gets, the taller it gets. So the age and the height, when one goes up, the other one goes up. That's direct. And then they give us a formula. They say, well, the formula for a direct proportion is y is equal to kx, and k is a constant of proportionality. And then there's our variables. And so, again, if you're not really a math person and you look at that and you think, well, I don't know how that tells me a direct proportion. I see pictures. I know how arrows tell me a direct proportion, but I don't see it in the formula. Well, then play with your formula just a little bit. Y is equal to k times x. Well, let's pick a number for the constant, and I'm going to pick k is equal to 3. I'm going to make my constant 3 this time, okay? So if my constant is 3, then I'm going to pick some number for y. So I'm going to say, okay, y is equal to 6. And I have this y is equal to k, the constant, times x. So that means that 6 is equal to k, which is the constant, 3, and there's my x. Well, 3 times something has to be 6, so that means over here I've got x is going to be 2. X is equal to 2. So I have some numbers there. I made my constant 3. I have 6 as my y. I'm going to increase that. Let's make y 9. Now I'm going to put that into my formula. 9 is equal to kx. My constant is 3. There's x. 3. What could x be? Oh, look at that. 3 times 3 is 9. So now what happened is when I took my y and I increased it, my x also increased. There's the direct proportion. And then if I say, okay, I'm going to take y and I'm going to lower it. It was 6. I'm going to bring it down to 3. So now my y is 3. And my constant is 3. I'm using too many 3's. And I have 3 times x. So now 3 times what is 3? 1. So here then, x became 1. So what happened then, when I lowered my y dropped. So these formulas do check out. It works. And sometimes when you're not that comfortable with the math, before you start putting big numbers into an equation, play with some small numbers and get the feel for how those equations work. And the same thing happens here. As chemists, we don't care about the constant at all. What we want to be able to do is make predictions. So if we know that y is equal to the constant times x, we need the constant to be on one side of this equation by itself. So I'm going to then divide both sides by x, and that is going to get me y over x is equal to the constant. And if I'm not interested in that constant, but I know that I may want to figure out what happens if I change y, where will x be if I have two initial situations, and then afterwards the y is going to be y2 and the second one's x2, that if I take the initial y divided by the initial x, it's going to equal that constant, whatever that constant is, and then that would be equal to, after the change, y2 over x2. This is actually what Charles' law looks like. Okay, so when you see it in a lot of chemistry videos and a lot of chemistry books, they give you, well, I'm going to get rid of the y's and the x's. With Charles' law, it's temperature and volume. So they have T1 over V1 is equal to T2 over V2. And that's how you get this formula for Charles' law. And you saw that in the last lesson. So the thing about this formula here is that it has fractions in it. And we're not always comfortable with that. So sometimes when you see a video about Charles' law problems, you're going to see this equation. But if you cross multiply, V1 times T2 is going to be equal to T1 times V2. You get this formula. And this is the formula that I always use, because it gets the fraction out of there. The thing that you have to understand about this is it looks a lot like Boyle's law, only whenever temperature is involved in one of the gas laws, the temperature is going to be alternated. So it's T2 times V1 is equal to T1 times V2. This is the formula we're going to use for Charles' law. Again, the second temperature, not the initial, times the initial volume is going to be equal to the initial temperature times the second volume, and you should write that down. And here's a statement of Charles' law that you might see in a textbook. It's a direct proportion. If you printed out your worksheet that I sent, you will have this example in front of you. And so we're going to look at this example first. And one of the things that you have to remember when we're working with Charles' law, you have to convert all of your temperatures into Kelvin. So that's going to be an important part of this. The first thing we're going to need to do is make our temperature conversion. So we have 57 degrees Celsius, and we're going to add 273, and we're going to convert that into 330 Kelvin. And then we have our other temperature. It says 150 degrees Celsius. My little circle didn't come out. And we're going to add 273. You learned to do that a couple lessons ago. And that is going to give us 423 Kelvin. So do that right away. All your temperatures have to be in units of Kelvin. So don't waste any time. Get that part done, and then you can move on with the rest of your problem. Now when I follow my formula, I'm going to put the second temperature first, not T1, the final temperature. So you're going to have to read these problems carefully. What is the final temperature? After the change, the temperature became 150, which is 423 Kelvin. Put that into my problem. What is the initial volume? The initial volume is 1.235 liters. So I'm going to set that equal to the initial temperature times the final volume. And they're asking us, what is the new volume going to be? So that's what we're solving for. My temperature, which is going to be my initial temperature, is 330 Kelvin. And then my final volume, you can put an X there or a V, that's what I'm solving for. So now all I need to do is solve for V. And I can do that by taking both sides of the equation and dividing by 330 Kelvin. That'll cancel. So now you're going to take your calculator and you're going to take 423 times 1.235, divide by 330, and what do you get? Your kickout number, 1.583 liters. You'll notice that has more significant figures than everything that we see. And so we do want to go back and think about significant figures a little bit. And if you see that your two temperatures are in two significant figures, that's really where you're going to want to go back to. So we'll round this to 2 to keep it simple. We're not going to nitpick significant figures here, but They are part of the overall story. So there we've done the example. And now you're going to go ahead and try to do your first problem, looking at what we did with the example. So pause and read the problem. And then I'm going to give you one important hint. It says, what is the final volume in liters? So you are solving for liters. And look what they gave you for volume. So you need to convert your milliliters into liters so that you have the correct units. All your units for volume should be the same as each other. Just like when we looked at the first Boyle's law, all of the units for pressure need to be the same in those. So 254 milliliters, if you know that there's 1,000 milliliters in a liter, that is going to then become 0.254 liters. That's a conversion that it's great to just remember, whether you use the move the decimal place method or the other method with factor label. So we're going to start looking to find the pieces here. Our T2, well, our temperature 2 is 140. Is that what we want to put there? No, we need to convert our temperatures to Kelvin. So our initial temperature is 52 degrees Celsius. We're going to add 273 to that, and we're going to get 325. Our second temperature, it's a good idea to label it sometimes, is 140 degrees Celsius. And we're going to add our 273, and then we get the final temperature. I'm going to not do much more with you. I want you to finish this one without me. Of course, you're going to start out. Don't forget, you're going to have your second temperature first. Which is 413 Kelvin. I'm not having the best of luck with this writing utensil. Okay, I think you can do this from here without me, and the video will ask you a few questions as we go along. This is a nice, neat review of the example instead of my writing. If you want to take a look at that, take a screenshot of that for your notes. What's the problem that you did? There is, of course, a similar formula for Gay-Lussac. I want you to notice that when we look at the formulas together, we have Boyle's law, and in a indirect proportion, the initial conditions are on one side of the formula, and then the final pressure and volume are on the other. But in both Charles' law and Gay-Lussac's law, with the direct proportion, we see that alternative of numbers here. And so we have the second temperature times the first volume In Charles' law and in Gay-Lussac's law, it's the second temperature times the first pressure. We're going to look at those three formulas together next week. And I did not include a Gay-Lussac problem for you to do today. You just have another Charles' law and then a review with Boyle's law. Let me know if you need anything.